let's do it. Okay. So thank you everyone for coming. Today I'm going to be presenting on the research that I'm doing, which is the applications of simulation and virtualization in evaluating the security of SCADA and ICS systems. So this is some work that I do with a lot of people from the Powerhouse, and we also have Luis and Saja and some other people who are interested in coming in and working on this project. So to start with, the motivation for our work is that industrial control systems are a highly target-rich environment. Large networks have a lot of multiple interacting parts. There's all these controllers that exist on them, and they can span these large geographical areas. There's also a lot of legacy components, like controllers that have been around for 20 years, protocols that have been around for 40 years. And because of the safety requirements, it's not necessarily as simple as them going and updating all their equipment because they have a lot of it, or it might be expensive, or they might not want to because they don't want to break something in a system that already works. In addition to that, these systems support critical infrastructures, right? So gas pipelines, power plants, manufacturing centers, military security systems, and this makes them desirable targets for those who want to do a lot of damage. People like terrorists or nation states or foreign actors could be very interested in taking down these pieces of critical infrastructure if they're interested in, international actions and stuff like that. So the idea is we want to build security systems, but testing them is, for cybersecurity, is not as common as it is for safety, right? So they've had these safety practices in place for a very long time with like gas and electrical systems, making sure things don't blow up, making sure people don't get electrocuted, making sure everything's safe, and making sure the workers don't get harmed, and making sure these systems remain up so that we always have electricity, we always have gas, we always have those things. But since the world has been shifting and these systems have become interconnected to the internet with Wi-Fi and with these Modbus systems now running over IP and TCP and UDP and stuff like that, they haven't really refined these processes yet for a world of cybersecurity and a world of cyber threats. And there obviously is a lot of work in this area because these systems are, I wouldn't say vulnerable, but because they're really big targets and really juicy targets for those people who want to cause a lot of harm. The issue is that even though these systems are pretty target rich and that we want to make sure that they're secure, it's very difficult to test our security on live versions of these systems, right? Because again, their goals are to make sure they're maintainable, make sure that they're available, make sure that no one gets hurt, and it's not really a good idea to go in and start, penetration testing on a live system, right? And that's a typical thing in cybersecurity, right? We always have some sort of simulated or fake system to penetration test. But I think my favorite example is this one like short white paper I read where they went into this factory and they were going to do a ping sweep just to see what was on the network, and for some reason the ping sweep caused the robot arm to swing around the factory and break a bunch of things, and actually caused them over $50,000 worth of damage. And so it's just kind of an interesting preliminary, it's not going to happen every time. And obviously if you ping sweep these systems, most of them are resilient enough that nothing bad's going to happen. But it's just the idea that something that small could cause that much damage. So the idea that we have is to use simulation to test these systems. And this idea of simulating SCADA is not necessarily a new practice that's never been done before, right? So Carnegie Mellon has something called SCADA Sim, which is used for training people on these systems, used for training and recognizing denial of service attacks and modeling some sorts of critical infrastructure. There's also a lot of other work that exists where people have tried to model these systems, they've tried to simulate these systems, and they've tried to do stuff like network attacks and denial of service. And there's also physical test beds that exist. So the question is, okay, so why are we at CSU going to build another simulator, right? Why are we going to try and do this again? And it's not that we're reinventing the wheel here, but it's that these other simulations have certain flaws that need to be worked on, or need to be built out, or need to be researched, right? And so part of it is the fidelity and the accuracy of these models. So many of the architectures that have been developed in the past are built by computer scientists, right? Because that's what we do. We build software and we make these systems. But they don't have the right engineering perspectives. So they might build a system, but they might not really have the engineers to say, okay, yeah, this system is realistic, or this is an actual electrical grid that would make sense, right? And I thought a really interesting quote that Dan Zimmerly at the Powerhouse talked to me about was, he's like, you want these systems to fail not because they're designed poorly, but because your cyber attack actually worked. And he's like, and that's an important distinction, right? So as computer scientists, it can be really easy for us to build a system that's designed poorly because we're not engineers, and then we go and attack it and say, okay, look how good our cyber attacks are, we broke this system. But in reality, we just designed a poor system that might not ever have been what we would see in the first place, right? So that's a problem in developing simulation. And so,
Brant, just one quick question, So in your mind, a simulation environment where we are testing cyber attacks, will that be different than, a regular, very high fidelity simulation environment in your mind? I mean, maybe you can answer that at the end of your presentation, but I just thought that I'll place it out to you, Yeah.
Yeah, I think that's a great question, right? How is this, if I'm correct, you're saying, how is this different than just using the existing high fidelity simulations that these engineers have built?
Right. Yeah. I mean, are there certain things that we have to build into the design, so that it is,
Yeah. So
it doesn't break, maybe. Yeah, maybe it doesn't break. Yeah, go ahead.
Yeah, in some respects, yes. Right. Okay. So the way that really we're building it and the way that it actually exists might not be an exact one-to-one, right? And they have these engineering simulators, and the goal is not to reinvent them, right? The goal is to go ahead and build upon what already exists to add this cybersecurity control layer to it, and then be able to test cyber attacks on that, right? So the idea is that if you make it modular enough, right, you can take existing components and mix and match. And so you don't want to go and try and completely rebuild every single thing. You don't want to build your own physical simulator. You hopefully don't want to build your own PLC simulators all the time, and you hopefully don't want to rebuild all these HMIs, right? So in our work, we kind of are doing that to start with to create this proof of concept. But the idea is in the long run that you can go and mix and match these existing components. And so in some respects, I'm not going to say it's entirely different than what already exists, but what makes it different and what makes it powerful is the ability to have some modularity and the ability to kind of build it out with all these different components. And so when you're developing for cybersecurity, I think that it's a little bit different than the engineering thing. So you still want the system to be designed to function how it would function. But for example, in our gas pipeline, there are scenarios where there needs to be control intervention to prevent the system from failing. Now, if you were to model it as an engineer, you would just put a mathematical function inside the simulation that says, if this happens, then flip this valve, or if this happens, up the pressure here. And it's almost an instantaneous, or maybe you add some simulated delay. But when you're doing it with the cybersecurity scenario, what really happens is that some sensor triggers, hey, pressure's low here, that gets relayed to a controller, which is either pulled or sends some Modbus data to someone out in a control center, and that control center person then does the operations manually. And so the difference here is that there's this whole communication that goes back and forth versus just having it built into the model. So to continue where I left off, so it's about this fidelity and accuracy, which is a very debatable point. It's also about considering a broad scope of attacks. So a lot of these previous models, they talk about denial of service, they talk about network attacks, which are very common things in the cybersecurity world. But there's not a lot of work talking about attacks on the actual control loop itself. So there's all these people who do control system engineering, and there's known oscillation patterns and issues that occur when things get out of sync, or the timing is off, or the measurements are bad, or the commands are injected in a certain way that can cause these systems to break. So what they talk about, like at the Powerhouse, is like really when they did that. What am I thinking? That worm attack they did on that Iranian nuclear program or whatever, right? Yeah. It wasn't that they just ramped these things up and then broke them. What they really did was they would spin them so they would oscillate in this kind of unhealthy state for the motor, and then they'd slow them down, and then spin them up and slow them down. So it really didn't look like the system was functioning too far out of bounds, but what was happening is it was wearing down the motors on these centrifuges. And so the idea is the same in these systems. Is if you're really, really smart, you don't just shut the system off, or you don't just break something. You cause these oscillating states, or you cause these invalid states that may seem valid to an operator, but are actually causing damage to the system. So that's where I think a lot of work in ICS security needs to go into, is how do we combine our knowledge that exists of these control systems and what behavior shouldn't occur, and then prevent, attackers from doing that to our system. And so that's where I talk about the modularity is, if we can take existing things, like I was answering your question with, and integrate those into our model, then we don't have to build our own engineering simulator. We can extend that. We can add our own PLCs. We can go out and buy PLCs. We can code some virtual PLCs. And this way we can take what we had in previous simulation, which was something very rigid, and make it something much more flexible. Mm-hmm. So where does our work fit into this? We're trying to design and architect a simulator from the ground up, but to make it modular, and more modular than it is in other research. Be able to integrate these different things eventually, be able to have different HMIs, virtual and real PLCs, leverage the existing infrastructures. So MATLAB and Simulink is what we use for our stack now, but eventually in the future it would be cool to be able to use OpenDSS or PowerWorld or these other existing simulators and leverage their ability to simulate the physical world and then add our cybersecurity perspectives to that. Mm-hmm. Also, I find it really important that in our work we consult with engineers and actual cybersecurity experts to determine what are the important design considerations of these models, which attacks do we think need to be explored, and how should these physical systems actually operate, instead of just making wild guesses. Mm-hmm. So, important considerations for designing these simulators. So, like we've talked about, integrating with existing physical and engineering simulations is important. So that's why we're using this MATLAB SimScape stack to model our model, which is a gas pipeline. We want to use vetted and existing simulators that prevent us from reinventing the wheel, like I talked about. And if we use something that's super extensible, like MATLAB and Simulink, part of the reason I chose to use this and why we're using this is that it doesn't just model gas pipelines. We could model electrical grids. We could even model a manufacturing plant if we really wanted to, or we could go ahead and model even the dynamics of a heavy vehicle and then try and do some ECUs on that. So the idea is that you have this extensible physical model, and when we talk about this kind of 3-layer architecture, it's like it's not just limited to ICS. If you were clever enough, you could make this a pretty general model for any sort of embedded system where there's a control loop. All right, so other important considerations. We need to find ways to validate these models and make sure that they're realistic, right? So there's different ways of doing this in ICS. You might create actual physical models and compare your system to it. You might create your system to replicate an existing system and compare how they act in certain scenarios. You might use advanced math to validate and prove that, okay, this is realistic and this makes sense. Or you might even go and capture packets that flow in your simulated network and compare that to a packet capture of a real system. For us right now, we're not at that stage where we can really do a lot of this really effective validation. So we're currently just consulting with experts that we know in the gas system world and engineers to determine, hey, does this pass the eye test? Does this make sense? Is the diameter of this pipe the right diameter for the amount of gas that flows? If a hacker were to do this, would this reaction make sense in the system? So things like that, consulting with experts to start with, and then eventually when you have the right models, you can go and actually do these more rigorous validations. Scaling simulations is also very important. So previous work has built either really large-scale simulations without much granularity, or they've built really high granularity simulations, but they're very small. So is there a way that you can kind of get the best of both worlds, where you can have simulations that can model entire gas pipelines or entire regional electrical grids without losing your accuracy and still being able to be computationally efficient? So that's an important consideration. And in our model, we're trying to model eventually the entire Colorado gas system. We haven't run into too many issues with performance, but I think it'll be an eventual hurdle that will have to be addressed. Mm-hmm. Okay, so other considerations, simulating long-term behaviors. So, for example, in our gas pipeline, things don't just happen instantaneously, right? So gas actually takes time to flow over 150 miles or whatever. So if someone shuts off a valve or if a compressor goes down, that change takes hours and sometimes even days to propagate through the system. So it's important that you're able to simulate, weeks and months at a time very quickly, so that you're not just sitting there in real time saying, hey, we're going to check on our simulation in 5 hours to see what happened, right? Of course, there's some issues with this in our simulation now. So we run about a week of gas simulation in the course of 2 or 3 minutes. And what happens is we run into these timing issues where any delays in the network are magnified by the ratio of simulation to real time. So if the simulation does 5 minutes in 1 real second, then a delay of 1 second will now become a delay of 5 simulated minutes. So that's a very simple example, but that means that timing becomes very, very important in these models and something that needs to be considered. Integrating hardware in the loop is something we want to do eventually. So I think that's some work that Luis might even be working on in the future, which is, okay, can we take some PLCs that we've written as, Python processor or whatever, but also go out and either buy a Raspberry Pi and put OpenPLC on it, or go get a real PLC, hook it into our simulator, and find a way that we can have some real, some virtual, and hybrid PLCs and stuff like that. So by doing that, we get this more realistic model, because now we can actually try and attack those physical PLCs. And then finally, a long way off, but if we can model the network, the SCADA network itself, and not just do Modbus, but have an extensible way to do DNP3 and be able to look at different protocols, and then with that, we can model network delays and also different network type of attacks. Okay, so cybersecurity, in our simulation, we look at basically measurement attacks is the focus of my research, but we could do what is called a command injection attack, and then there's other control loop feedback type stuff we could do. In the future, we would love to be able to do ransomware and denial of service and network attacks and malware and worm propagation, but our model's just not quite there yet. So we'll focus on these measurement and command injection attacks. So what is a measurement attack? Essentially, we're attacking the control loop and its feedback. So what we have down at the bottom here is our kind of control loop. So we have basically a controller that has some ideal state, which is mu, and then it computes some function, which is the difference between mu and mu prime. So the red thing is the state we get out of the model. The black mu is the ideal state that we want. So our function is usually some difference between these, or some kind of cost function. We use that to adjust the state of the physical system, and then hopefully reach our ideal state. Now, what happens with a measurement attack is that we compromise this mu prime that comes through the model. So what happens is we start giving false measurement back. So even if the state is ideal, the controller might not even realize the state is ideal, and so they're going to take control actions based on what they think is going on instead of what is actually going on. So how do we design our simulation? So essentially, we have some critical parts of the design that we'll go over. A 3-layer architecture, which is essentially we have a physical component, a control layer, and then either an HMI or an operator layer, which we'll talk about a little bit more in a second. The ability to interface with Simulink and Simscape is a critical part of our design. Finding ways to design gas pipelines that are realistic. Resolving timing issues, like I talked about earlier. Simulating some compromises and simulating some measurement attacks, and then being able to use something called an Oracle PLC to get ground truth data out of the model so that we can compare our actual falsified measurements with the real measurements in the system. Okay, so let's talk about this 3-layer architecture first. So over here you can see on the right that we have basically our physical process. So that's our Simulink model, right? That's our gas pipeline. And then what we do is we'll use some UDP blocks and some data channels to extract data out of that model and push it into our control layer, which is where we have our Simulink interface. Simulink interface spawns up several virtual PLC processes, and they communicate to the interface through some shared memory. So what happens is, let's say there's a pressure sensor in the physical model, and it reads 600 psi. That 600 psi measurement gets relayed to the Simulink interface, and then the Simulink interface dispatches that reading to any PLC in the system that would be listening for that sensor. So it allows us to have multiple PLCs listening to one sensor, which isn't always clear why that'd be useful, but it so happens that we can extend these PLCs to become like an Oracle, or if we have some other system that wants to listen to the same data channel, we can just have them all register to listen to that. Then what can happen is any control actions that these PLCs want to take get relayed back through the interface, and they get sent back into the model. So we have this kind of control loop. Then we have a SCADA network, right? So these PLCs are Modbus servers like they are in the real world. They can talk to an operator. So the operator uses Modbus to query these virtual PLCs through the SCADA network. They get data or other things out of them, and then they can actually send control signals through the SCADA network as well. And so that in that way they can interact with these PLCs like they would be interacting with them in a real system. And then, so let's say if the operator says, hey, I want to set the output pressure of this compressor station to 800 psi, he sends a Modbus request through the SCADA network to one of the PLCs. That PLC then relays through the interface into the model and updates that reading. And then in this way, we can have a control loop between the operator and the physical system. The Simulink interface, which is how we actually get all our virtual PLCs and stuff to talk to our Simulink simulator that's an existing engineering simulation. So it has some UDP sockets that listen, and it kind of is this select server that basically dispatches this data to all these PLCs that are listening. And so we have some PLCs that have workers inside of them. And so the worker is listening on a channel. So if, let's say, some sensor in the model sends data over UDP port 8080 to the Simulink interface, then let's say this PLC auxiliary power PLC is listening for data coming on the 8080 channel. So that worker inside of that PLC is listening for it. And they can have multiple workers. So they can have one that's listening for temperature, one that's listening for pressure, one that's listening for control signals. And so these PLCs, essentially, you can think of the worker and the connection to the Simulink interface and the actual model as like a physical wire. And then the worker is being like the port that the wire plugs into. And then the PLC is the actual PLC that operates over these physical channels. And then it has a Modbus server. So they essentially use shared memory to communicate. And then this interface communicates with the actual physical model. And so then how do we simulate these measurement attacks in the system? What we do is we take our workers that exist inside of our PLCs, and we just in our configuration, we can configure them to be compromised. And so that all we do is slap on a compromised layer to the existing worker. And so in this way, we don't have to redesign every single thing. We just add this compromised layer, and this all it does is if the reading is considered, right? So if the reading that the worker is getting is X, or I'm sorry, if the reading that the worker is spitting out is X, then the reading that the compromised worker is spitting out is some function X of T. So what that means is that we take the actual reading and the current simulation time and we modify it by some, some expression. So we might take all the readings and subtract 200 from them to say that the system's reading lower than it actually is. Or we might take some function of time and X and have it decrease over time so that it looks like this sensor is slowly showing that the pressure is decreasing over the state of a couple of days and things like that. So it makes us basically able to just plug a mathematical function in and be like, okay, this is the compromise that they would try and attempt. All right, so then what I talked about earlier is the Oracle PLC. So the thing is that if we're going to throw these compromises in the system, we're going to have some places where there's compromised data. But it's also the case that when we're creating our graphs and running our experiments, we also want to be able to see the real state of the system. So we'll have some compromised readings, and then the Oracle PLC is just another PLC that's registered to listen to every sensor channel. And it's a Modbus server like all of them, so it can be queried with Modbus. But this thing, basically, we set up so that it's never going to be compromised. And that way we can retrieve ground truth data. So let's say if there's one sensor in a power plant that's being compromised to read something false, that the PLC that's normally on that sensor is going to be sending that false data. The Oracle PLC is just going to be registered to listen to that same channel from the model, but this one is going to be sending the non-compromised reading so that you can compare the two. The Oracle PLC also has a kind of a time server running on it. And this way the front-end operator can get a sense of what simulation time is. And so when we're running our control loops, we know, okay, we need to wait 5 minutes of simulated time. So since there's the Oracle PLC giving you time updates, you can actually say, okay, we're waiting for an hour of simulated time. You're not just making a guess of like, okay, sleep for 10 milliseconds and hope that translates to 1 hour of simulated time. So how do we propagate time through the model? Like I talked about, we use this Oracle PLC. Simulation time is a concept that's really only native to Simulink, and so as a result, we have to extract the time out of this simulation and propagate it through our system so that we have some sense of time and some sense of how everything is operating. So what we do is every time we send out a sensor reading out of our simulation, we also have a timestamp with that sensor reading, and that way each PLC updates the current time each time it gets a new reading, and then the Oracle PLC is designed to also be able to send that time to the operator of the system. The main flaw with this approach is that we have no way of actually controlling the time. Someone post something in chat. Oh, Jared's leaving. Okay. The flaw is that we're just playing catch up the whole time. So the simulation is chugging along, going as fast as it wants to go. We're getting time updates and trying to operate based off this time, but there's no guarantee that the simulation isn't going to jump forward or start moving fast for performance reasons. And so really, the issue we have is that we can only try and contain some of these delay issues that we have. And in future work, the goal would be to find a way to actually be able to halt everything, propagate the new state, and then advance, right? So that we aren't playing kind of fast and loose, but we're actually having some rigid sense of time throughout the model. And then that way we can control delays and make those delays more realistic. Because what happens in these systems is that, like, if there's an operator in Texas and he needs to flip a valve in Colorado, there's some delay that occurs. And that delay is important to model in the system because that can be an important difference maker and say, like, if they need to get these gas systems online within an hour and there's a 2-minute delay between every control action because they're heading so far away, that's an important part of the simulation because that can have real effects on the physical system. All right, let's go forward a slide. Ooh. Okay, so how do we model gas pipelines? How do we make them realistic? There's a lot of considerations, right? We have to have pipes that are sized to deliver the right amount of gas. We have to have the gas set at the right pressures. All these things that me as a computer scientist, I might not natively know, right? So we have to have realistic demands. We have to have compressor stations that compress with some realistic amount. And most of this work is done by talking to engineers at the CSU Powerhouse. So I go and ask them, I'm like, is this model realistic? And then they talk to people they know in the gas industry and they say, yeah, this model looks good, or no, like it's more realistic for you to have a pipe of this size or to have multiple pipes, or this is a more realistic gas demand on the system, or realistically this controller can only do, or realistically this compressor can only compress this much gas, and so on and so forth. So this is kind of an iterative process of me talking to engineers and stuff and trying to figure out what looks realistic. So obviously in future work, if you have the right engineering perspectives, you could hopefully make this process easier. But for now, we're just trying to build something that is realistic enough that we can start to make these cybersecurity tests. And the system doesn't just fail because we designed a bad gas system, but because there's actual cybersecurity or control flaws in the system. So finally, we need to model the pipeline operator. So this is the person sitting behind a desk, working on the control system, turning valves on and off, updating compressors and stuff like that. So our main model just has essentially what is like a Python script that reads sensors inside of the system, and then they update the PLCs to say, hey, update this compressor if the pressure is too low downstream, or hey, in some cases you could say, hey, pressure is too high, open this valve to vent pressure or something. We also have to model some safety scenarios. So, for example, with these power plants, if the pressure is too low or the temperature is too low, they'll actually shut off for an hour. Because, for example, if gas pressure drops really rapidly and temperature also drops rapidly, the gas can actually freeze, and it becomes essentially what they describe as shotgun pellets flying through this gas pipe, these frozen gas pellets, and that can cause a lot of damage to the system. So if they see temperature dropping rapidly, there are scenarios where they'll actually shut off to make sure that the system's not damaged, and then they will wait till the state is more it's more safe to continue to run, and then they'll turn their power plant back on. So on our simulation, we'd say, okay, now shut this power plant off in the model, wait an hour, and then turn it back on or something like that. So we have to be able to model that with our operator as well. So here I have a small scale example model of what we're working on currently, and this is a Simulink model. So in this, you can see on the left side, we have our upstream. On the right side, we have our downstream. This is possibly the simplest case of a model that I can demonstrate, where we have basically gas flowing through a 50-mile pipe. That pipe goes to a compressor station, which will compress that gas to maintain its pressure of 600 psi. And then it flows through another pipe downstream to a power plant. And this power plant has some gas load where it consumes, let's say 40 kilograms of gas a second, 50 kilograms of gas a second. And as that load goes up, it causes the pressure in the pipes to drop as it's pulling gas out of these pipes. And then the control loop, the operator sees, hey, pressure's dropping, this power plant's consuming more gas, I need to compress more gas, push more gas down the line, essentially. So in this small model, we did a small measurement attack to demonstrate the principle of it, but it's not necessarily the most realistic thing that exists in the world, right? Because we have one power plant and one compressor. It's not really enough complexity to demonstrate how effective these attacks can be, but it's enough to show the idea behind them. So here you can see this blue line is the compromised reading. So this is if you were doing a measurement attack and you were sending false readings to the operator, this is the reading you would be sending. The green line is the actual pressure at that power plant, and the orange line is the actual temperature at that power plant. So what happens here is you can see that the attack triggers about halfway between day 0 and day 1. And as that attack triggers, it just gradually starts to read lower and lower pressures over the course of the next 3 days. So basically saying, like, this power plant's losing pressure slowly, right, over the course of days, not instantaneous. But what happens now is the operator is trying to up the upstream pressure in order to compensate. So we see that the real plant pressure is actually going up to 800 psi because this operator is trying to get more gas down the line, but we continue to read a compromised pressure reading and lower and lower and lower, and then eventually the plant will shut off about some way between the 3rd and 4th day. But it's important to note that in this simple example, even if we're compromising this pressure to read lower and lower, you can see that the temperature isn't changing, right? Because we were only compromising this one sensor in the system. And so it's interesting to show that you can even see that the temperature goes up in certain cases where the gas pressure is going up, which is part of ideal gas laws. And so I find this really interesting because it means that even if you were compromising the pressure, if someone was a clever operator, they could know that this is an invalid situation, because if pressure is dropping as consistently as it is, you should also see some change in temperature as well, which you're not seeing. And so that could indicate a faulty sensor in the system. But a clever attacker might be able to compromise both the pressure and temperature sensors because they might be on the same PLC. And then they can actually have those vary together to make it a more realistic type of scenario where the operator might not be able to tell that this system is being compromised. So really to show the effect of these measurement attacks, so this model is very simple, right? There's one power plant. It's not very realistic because obviously they're going to have redundant sensors. Obviously they're going to have all these other things going on that they can tell that something's wrong. What we're going to try and do is now that we have this main principle down is, okay, let's create a large scale model and start playing with measurement attacks on this model. So what we do is we need something pretty sophisticated. And so what we're trying to build out right now is we're trying to build a gas pipeline gas simulation model that is the gas system in the state of Colorado. So what that means is, 10 power plants, maybe even more than that. But we're mostly just simulating kind of this part east of the Rockies. But then we have, almost 1,000 miles of gas pipe, several compressors, a lot of sensors, a lot of PLCs running. We have cross connections. So if, let's say Denver power plant, right, they need to crank out more power. They're not just going to draw gas from Fort Collins and Longmont. They're also going to draw gas from Fort Morgan and other areas. So they're actually drawing gas from multiple pipes. So we have this kind of branching structure, which means that there's some interdependencies that occur in the system. And so if you can kind of compromise certain points strategically and do things the right way, you might be able to get the system to go into these invalid states that can then cause power plants to trip off and cause the system to fail. So the scenario that we're proposing, that we're working on to try and be our kind of proof of concept scenario, here's kind of a measurement attack applied in a real system. The idea is that, like in Colorado, sometimes the load of the power system can be carried by wind farms. Like sometimes 80 to 90% of all the power in Colorado might be being generated by wind farms. But the thing is that there's situations where this wind will actually die down over the course of an hour or two. So all that power generation kind of just goes away, and the system starts leaning on the surrounding electrical grid. And then what happens is that they need to get these natural gas power plants fired up over the course of a few hours. And so they start ramping up these gas loads. These power plants turn on. They start all needing gas at kind of the same time. So what happens is in this scenario, all these power plants turn on. They all need gas. They're all trying to generate power. So they're sucking gas down these lines. And a manual operator has to be able to say, okay, I see that, all these loads are going up. Pressure in the pipe is going down. So they're going to ramp up the compressors to compensate. And so the idea that we have is, okay, if you were a really intelligent attacker or a hacker, you would camp out on the system for months, and you would watch for these types of scenarios where you see that the system is under high level of strain, right? So all of a sudden everything has to turn on. They have to pack these lines with gas. So you wait, and you wait for one of those scenarios. And then what you do is you delay some of the control actions. So you either make sure that these readings are coming in a little bit late or a little bit off or reading a little bit higher in several different strategic locations, so that they don't quite ramp up the gas load to where it needs to be. And what happens then is, the weakest power plant in the system, let's say, the one the farthest downstream that might be the most vulnerable to running out of gas first, right? They run out of gas and they have to turn off. So you lose 500 megawatts of power. So now that has to be made up somewhere else in the system. So now these other power plants in the system have to ramp up. So then the next weakest one might then run out of gas because you're kind of delaying these measurements of how it needs to be ramped up. So that turns off. Okay, so then that load has to be taken on by the system. So it starts to cascade. And so the idea is, can we show that we can start to get some power plants to trip off in kind of this cascading manner by delaying some of the measurements in the system, or by lying about some of the measurements in the system to the operator. So that's kind of where the direction we're headed in. We're not quite there. We're currently building the model, and then once we have that built, we're going to start trying to apply some of these measurement attacks to kind of demonstrate this behavior. But we're still a few weeks off from that. So some other future work aside from doing that we want to do with our modeling is we want to build a model networks and network protocols so that we can do denial of service attacks like other simulations can. We can do other network-based attacks. We want to integrate that simulation clock that I talked about so that we can have time that is more rigid, and so that we're not playing catch-up, and so that we can actually control the delays in the system to model realistic delays. We want to be able to integrate hybrid and real PLCs into this model so that we have higher levels of accuracy and fidelity and make this system more realistic. And then we also think it would be interesting to use machine learning or maybe some sort of statistical methods to look at how could you detect if one of these sensors was faulty or lying, and is it even possible? So this is kind of one of those, in some respects, it's like a Byzantine generals problem, right? Where if some of the parts of the system are lying, are you still able to kind of tell what the actual state is? I think the most interesting application of this would be some sort of constraint discovery, where you can automatically discover constraints that exist in the system. So for example, you could discover a constraint that, power plant A and power plant B, their pressure and temperature usually vary together. And so if they're not varying together, that might indicate some sort of inconsistency in the system. Or for example, when we talked about pressure and temperature varying together in a single power plant, that's another constraint that might exist. And if you could discover some of these constraints automatically, you might be able to then apply them to detecting if someone is inside of your system and trying to falsify stuff. Now, obviously, really, really intelligent hackers should also be able to know these constraints and be able to, work their attacks around that. But I still think it's interesting to know because it even has certain implications for safety if a sensor is faulty or broken or something like that. And then something that I also think would be interesting is, since we have this simulation, we can do pretty much anything we want with it. So why not try and add encryption to these, Modbus protocols or something and see how it would look, see how it could prevent X or Y type of attack. Not that we could go out and put these encryption schemes on real PLCs in the real world willy-nilly, because obviously there's certain problems that exist with that, like having these legacy infrastructures and stuff like that. But it's still an interesting case where you can say, we've come up with a way we would do encryption. This is how it would look. This is how it would prevent attacks. And at least you have some sort of data and some sort of system to show how it would work. And then finally, we want to eventually start to create some more physical models, so electrical grids and stuff like that, and even being able to plug and play these into Simulink so that we have a larger portfolio of work that we can demonstrate these types of ICS attacks on, stuff like that. So kind of the end of what I've got so far. I'm now open to kind of answering some questions and discussing about this, what you guys think about it. What do you guys think could be better? How can we improve this system?
Questions? So, one of the things that occur in my mind is like, when you're building a modular simulation systems, how would you go about deciding the granularity of the module? What constitutes one logical unit and things like that, So, and secondly, in light of, say, we want to, build a test bed where we can study different kinds of cybersecurity attacks, will the decomposition and the modularization be different?
So to answer your questions, I think the second one, right, will the way that we build the system be different for different types of attacks?
Mm-hmm.
I think yes, because in some respects, right, you have to design a system to kind of explore what you're most interested in, right? So the system that we have right now is great for looking at measurement attacks. It's great for looking at command injection attacks, but it's not very good for looking at ransomware. It's not very good for really modeling how an attacker would get into this network. It's not really great at modeling how an attacker would actually compromise one of these PLCs, and it's not really great for modeling network attacks. But if you were to, add in some other components, then you could focus on modeling network-based attacks, right? And then to go with your first question, right, is how do you decide the granularity of these modules? Like, how do you decide, for example, if you're going to simulate the entire West Coast electrical grid, right, there's a lot of PLCs and sensors in that. Is it really wise to model every single one of them, or is it necessary, right? So you might go in and say, okay, these 1,000 PLCs act in this consistent, predictable manner. And then maybe you have a few set points which you want to look at being the points of attack. And so I think it definitely depends on the type of experiment that you're running on the system. And so the goal here is that if you kind of had some modularity, you could kind of set up a scenario that's realistic enough using some modules, right?
Mm-hmm.
Right. So you have your physical model, you have your control layer, you have your operator interface. You set up a realistic enough situation, and then you show how this kind of attack could compromise that situation. And then you show some methods that you might be able to defend against it. So it's not going to be a perfect one-to-one ratio to the real world. Modeling never or rarely ever is, but it does give you a lot of intuition about what's going on, and it does give you a lot of intuition about what you can do to stop it, I think.
Good. And so what you're saying is that ideally we would like to have a repository where, we have all these modules, and you would, some kind of configuration information, and, like if you were to study this attacks, maybe you should plug these in and something like that, right? Because otherwise, I think the complexity of the whole thing is like, I don't know, I'm just thinking it might be too big.
Yeah, I agree with you. It can get really complex because these systems by nature are very complex, and they're very difficult to find a way to accurately model them. But if you could, right, in the long run, have some sort of repository of modules where you could plug and play, right? So this is what they do with SCADA Sim and the Carnegie Mellon thing is they do have plug and playable modules, but I don't think that they have the ability to integrate with these existing simulators, and I don't think they have some of the stuff that we're trying to put in. But yeah, so if you could really do that, or even if you could have preset models, right? So here's your gas model. Here's the type of attacks that you could explore on it. Or here's your electrical model. Here's the type of attacks you could explore.
Yeah.
And then you have some attack scripts. So you create this kind of pseudo deter-like structure of like looking at, this experimental situation and then seeing how the model reacts to it.
Yeah, I guess, yeah. So, Brant, and also in your thesis, because I think the Carnegie Mellon, the module that you talked about is the closest, right? I mean, and so what would be nice is if you can, enumerate explicitly some of the things which your thing will be able to do, which is not supported. That would be great, actually. Yeah.
Yeah, we can definitely do that. It's hard because they don't have it's really hard to find a paper on what they did. So it's very hard to determine the full capabilities of their system. But
so do you think like somebody who has access to such a system? I mean, can a student get access to for studying SCADA systems into their?
Yeah, I think they do have an open source thing somewhere, so I might be able to go and explore that a little bit more.
Okay.
And determine what you can kind of do with it and what you can't.
Yeah, and that kind of comparison might be useful, in your thesis or paper. So that's good. Excellent presentation, actually. And any other questions? Everyone's so quiet today.
None for me, but I think that was a great presentation, Brant.
Thank you.
I think it was very well done. Very well done. Yeah. Anyone else? Any other questions?
No, I don't. But that was a really good presentation.
Yeah, thank you. So
thank you,
who is presenting for next week? Do we know? Louis, are you up for next week's presentation?
Yeah, I can present what I was writing about, or I can choose one of the papers that I was writing on.
Yeah. And so we can confirm that, right?
Yeah.
So next week, okay.
Yeah.
And okay, so that would be good, actually. So and then the week after that, we can any volunteers for the week after that. How many weeks do we have left, actually?
Like 2 or 3, I think.
Yeah.
Yeah.
So next.
Stop this recording.
Yeah. So and a week after that, anyone